Thanks, Avi. Thanks, everyone, for coming. So I'll be talking about ordinary lines in complex space, and I'll tell you all what that means. This is based on joint work with Abdul Basit, Zev, and Charles Wolf. Abdul and Charles are students at Rutgers, and Zev everyone knows, and he's here. So let me start with the Sylvester-Galai theorem. Okay, so it's how many of you have seen the Sylvester-Galai theorem? Oh, basically everybody. So all but one.
So I make a point. It's not Sylvester. It's not his theorem. It's Galai and Melchior.
Galai, Melchior, maybe only Melchior. I don't know. So Sylvester. It's a classical theorem. All of you have heard it. It was 1893 was when Sylvester asked the question, and in the 40s, 50 years later was when it was proved. First proof by Melchior, and then it was reconjectured by Paul Erdős, and then proved by Galai, and it's called the Sylvester-Galai theorem. And let me quickly tell you all what it is, though you all basically know what it is. If you're given a finite set of points in the two-dimensional plane, and you're given the property that for the line through every pair of points passes through a third point. Take any pair of points, you take the line through them, it passes through a third. Then all the points must be collinear. That's the only way it can happen. I mean, it's a very classical theorem, beautiful proof. Many proofs are known today. It's very well studied. Many variations of this theorem have been studied, and I'll talk about a few of the variations. Recently, there have been connections to theoretical computer science, so arithmetic circuits, locally correctable codes, etc. I won't tell you too much of these connections today, but we'll just talk about the Sylvester-Galai theorem and some variations.
This is over the rates.
You can ask these questions over any field.
But then, okay.
You can ask, so all these questions, you can ask over any underlying field. These connections have been basically over the reals and over complex numbers.
When the Sylvester-Galai theorem is over the reals.
The Sylvester-Galai theorem itself is over the reals, Euclidean space, absolutely, yeah. But you can now study extensions to other fields, even finite fields, and you can still ask the question. Okay, so I'll talk about some interesting variations of the Sylvester-Galai theorem. We'll focus on a certain question over the complex numbers, and I'll say what that is, and then we'll see some proofs. And in the proofs, we'll see rank bounds for design matrices. That's going to be the main ingredient. So again, let me just set up some terminology. So suppose you have a finite set of points that spans two dimensions. So these points are not collinear. Then basically the Sylvester-Galai theorem says that there must be a line which passes through exactly two of the points. Because if the line through every pair passed through a third, then the points had to be collinear. Okay, so any configuration of points that spans the two-dimensional plane must contain a line through exactly 2 points, and we'll call such a line which goes through 2 points, we'll call it an ordinary line. And most of you have seen this Sylvester-Galai theorem, you must have seen a proof of it, but let me just very quickly give a proof, which was the proof discovered by Kelly. And again, it's a really beautiful proof, and let me just give it in one slide. So if possible, the Sylvester-Galai theorem is not true. And so you have a collection of points spanning the two-dimensional plane, and for every pair of points, if you take the line through them, it passes through a third point. Okay, so that such a configuration exists. And since all the points are not collinear, there must be some line determined by the points and some point which is not on that line. So now look at all these lines, look at all the points, and consider the point line pair with the smallest non-zero distance. Okay, so here's a point and here's that line, and they have the smallest possible distance between them. Now this line, we know that by contradiction we assume that the line through every pair of points passed through a third point. So this line must have 3 points on it. 2 of the points are on the same side of the foot of the perpendicular. And now here's a contradiction. You will see that the line through this point and that point, and the distance, this point line distance, is smaller than that point line distance. Simple, similar triangles, simple angle chasing will tell you that that's the case, and that's a contradiction because we started with the point line pair of smallest non-zero distance. And that's it, and so that's a contradiction. and hence the Sylvester-Gallai theorem is true. And if you see this, you'll see that the notion of the Euclidean space, so the reals, was used crucially in this argument in two places. One is to talk about distance between point and line, to talk about the notion of a distance. That's where the Euclidean distance got used. The fact that there are 3 points on a line and 2 are on the same side of the foot of the perpendicular, even this used some real ordering, and so the real numbers got used here as well. Okay, so that's the proof of the Sylvester-Gallai theorem. Let me just tell you some variations you can ask on this question of the Sylvester-Gallai theorem. Instead of points and lines, you can talk about points and higher dimensional planes. So the Sylvester-Gallai theorem said if you knew that your points span a two-dimensional space, then there's an ordinary line. You can talk about an ordinary plane being a t-dimensional plane containing exactly t plus 1 points. And there's higher dimensional analogues which say that if you have a finite set of points spanning at least 2 t dimensions, then there is a t-dimensional ordinary hyperplane. And this is over the reals. There's analogues of this over the complex numbers. This was these two works I'm going to talk a lot about. There was a paper, this is Barak, Dweir, Yehudayev, and they originated a very different kind of proof technique to answer questions of this kind. And then this was the work, this is Dweir, myself, and Avi. And basically this work refined the techniques in this to give strength and bounds. But this framework gave a very different approach to understanding these incidence kind of questions. And so this proof was again very specific to the real numbers. This technique gave weaker bounds, but we could talk about the complex numbers. And high dimensional analogues of the Sylvester-Gallai theorem had the connections to arithmetic circuits, which I won't talk more about. There's another question of the quantitative Sylvester-Gallai theorem, and I think this was really the question that the BDWI paper was interested in. And the quantitative Sylvester-Gallai theorem says not that through every pair of points the line through them passes through a third, but if you knew that for many pairs of points the line through them passes through a third, what can you say? And so we say a collection of points is a delta Sylvester-Gallai configuration if through every point and delta fraction of other points the line through them passes through a third. Then it's a delta Sylvester-Gallai configuration, and what this paper showed that such a configuration must have dimension depending only on this constant delta. And the techniques were again refined in this other paper, with an improved dimension bound, which was shown to be optimal also.
Sylvester-Gallai is delta equals 1.
Sylvester-Gallai theorem is delta equals 1. For every point and every other point, the line through them passes through a third. Here, for every point and many other points, the line through them passes through a third. And if you look at it carefully, this question is equivalent to two-query, in some sense, to two-query locally correctable codes. And this theorem, this result precisely says that two-query locally correctable codes over the real numbers do not exist. And it's almost identical to, if you translate it into the locally correctable codes language, they're saying the same thing. Good. You can ask, and there's another version which was studied in this paper by Dweir, myself, and Avi. Suppose you don't know that these points are exactly collinear, but approximately collinear. If for every pair of points, the line through them almost passes through a third point, then what can you say? Then you can say that these points are all approximately collinear. So not collinear, approximately low dimensional. I'm fuzzing a bit and maybe cheating a bit, but that's the spirit of what we could show. And these, you can translate them to an analog of stably locally correctable codes. I don't want to, this is just to tell you what all has been done. I don't want to focus too much. There was recently, Zev and Guangda had a paper on the Sylvester-Gallai theorem for subspaces. So what I do want to say is that both the earlier results, the stable one, this result also, the proof of this used these rank bounds for design matrices. The proof technique was very similar in this as well. In this, Zev and Guangda had a paper which talked about, instead of looking at saying for every pair of points a line through them passes through a third. So instead of asking lots of collinear triples, they asked for lots of dependent collections of subspaces. For every pair of subspaces, your collection of subspaces, and for every pair of subspaces, their span contains a third subspace. What can you say of this? What can you say about this collection of subspaces? And they showed that the collection of subspaces needs to be low dimensional. And again, the proof was, this was an extension, another high dimensional extension of the Sylvester-Galai theorem, and the proof again used some variations on the rank bound technique. The other extensions you can ask for colorful versions, average case versions, but again I don't want to, so that was just a flavor of what all is out there. These rank bound techniques have been really powerful in understanding several of the works I talked about. Let me now maybe start focusing on the question I want to discuss in the talk, and Melchior's inequality is one particular inequality I want to draw attention to. So the first proof of the Sylvester-Galai theorem was given by Melchior in maybe 1940 or 1941, and basically Melchior proved the following inequality, and the Sylvester-Galai theorem falls out immediately from this. If you have a configuration of points in, say, the two-dimensional Euclidean space, let T2 is the number of lines through exactly 2 points. So that T2 is the number of ordinary lines. TR is the number of lines through R points, the number of lines which contain exactly R points. Melchior showed that T2 is at least this quantity, 3 plus the sum over R being at least 4R minus 3 times TR. And the proof is not very difficult. This proof of this inequality basically uses this V minus E plus F equal to 2, the Euler characteristic, and you look at a suitable graph and you sum over cycles, and you do look it carefully, and this is an inequality that he can achieve. And this immediately tells you that the number of ordinary lines needs to be at least 3, possibly larger than 3 if you have many lines which are 4 rich or more. So I'll call a 4 rich line a line with 4 points, 5 rich line is a line with 5 points. So if you have many 4 rich lines, then you can get perhaps more ordinary lines, otherwise you get at least 3 ordinary lines. And so it was an interesting question to now see, okay, the Sylvester-Galai theorem says that there must be at least 1 ordinary line. Here you get 3 ordinary lines. How many ordinary lines can you guarantee? What can you say about the number? And there was this collection of works showing strengthened lower bounds on the number of ordinary lines, and then in 2013 Green and Tao basically resolved the question completely. They showed that if you have n points again spanning 2 dimensions, then there must be at least n over 2 ordinary lines, and this is tight. For even n they showed it was n over 2, for odd n they showed it was 3n over 4, and you have matching upper bounds. So there's configurations of points which match this exactly. So this exactly resolves the question of ordinary lines. They used Melchior's inequality in their proof and a whole bunch of some algebraic geometry, a whole bunch of very beautiful techniques went into giving this tight bound on the number of ordinary lines. But again, this is again very specific to the Euclidean space. The proof really used properties of the real numbers crucially to get this bound. Okay, this is tight. Good. Now let's go again revisit complex space. So I mentioned that some of the results were also known over the complexes, but so just first off, the Sylvester-Galai theorem itself is not true over the complex space. So you can look at 2-dimensional complex space, and you have complex points in it, and you can talk about complex lines, and it is known that you can have a finite set of points in 2-dimensional complex space such that the line through every pair passes through a third, and these points are not collinear. So there are such configurations. So the Sylvester-Galai theorem is not true.
You can say elliptic curves, for example.
Elliptic curves. Elliptic curves are what I use in this. So you can just inflection points of certain cubic curves give you configurations of points which give you such configurations. this configuration is the Hesse configuration, but you can have generalized, I mean, for every n, you can basically have a configuration with n points achieving this. And so though the Sylvester-Gallai theorem is not true, what Kelly showed was that, I think, and this is maybe 1986, if you have points spanning three-dimensional complex space, then there must be at least one ordinary line. So in Euclidean space, if the point spans 2 dimensions and there was one ordinary line, in complexes, if they span 3 dimensions, then there must be at least one ordinary line. In particular, if you knew that if you have points sitting in higher dimensional space, and you knew that if the line through every pair passes through a third, then the only way that can happen is that the points must be 2-dimensional. The moment they span a higher dimension, there must be one ordinary line. And this original proof of Kelly is like, we saw the Sylvester-Gallai theorem proof. It was just one slide. It was extremely simple, elegant. The proof of Kelly's theorem, the original proof, used quite fancy algebraic geometry. I don't understand the proof. It used an inequality called the Hirzebruch's inequality, which I will mention in a later slide. But this proof is significantly more sophisticated than what was needed for Euclidean space, where the arguments were much simpler. Then there was, in 2006, Elke's Pretorius van Poel gave a much more elementary proof of Kelly's theorem. And in the paper, the same paper I talked about with Zev and Avi, using these rank bounds for design matrices, we managed to refine the bounds and get almost optimal bounds, and this gave a reproof of Kelly's theorem also using these rank bound techniques. Okay, so what I want to talk about is this new work, which is a strengthened version of Kelly's theorem and actually uses all these rank bound techniques. And what we show is the following, that if you have points spanning 3-dimensional complex space, then you actually have 3n/2 ordinary lines. So Kelly's theorem guaranteed one ordinary line. We say there must be at least 3n/2 ordinary lines. And this is in general, other than in the trivial case, suppose you put n-1 points on a plane, and you take this Hesse configuration or something so that there's no ordinary line in the plane. So in the plane, the line through every pair passes through a third. So you take such a configuration in the plane, and you take 1 point off the plane. Then the only ordinary lines will be the ordinary lines through this point and the other points on the plane. So then you can get at most n-1 or exactly n-1 ordinary lines. So other than this case, where you have n-1 in a plane, on all other cases we show that there are at least 3n/2 ordinary lines. And we don't know if this is tight. So this number 3n/2 is something that comes out of all the calculations. And like the green tau result over the Euclidean space, they show that there are at least n/2 ordinary lines, and we know that that's tight because we have configurations which match that. For 3-dimensional complex space, we don't understand, at least I don't know if anybody's looked at this question, and whatever configurations are known over the complexes use again these elliptic curves, and we weren't able to come up, at least with a little bit of trying, for any non-trivial configurations in 3-dimensional space. So it could be tight, but it's possible that much stronger bounds are true. It's possible that actually maybe there are a quadratic number of ordinary lines, maybe. So I really don't know idea if this is true, if this is tight, or what the right answer is. Good. Here's another result that we show. Suppose you knew, so 3n/2 lines we can show always. Suppose you knew that in addition you have many 4-rich lines or many 5-rich lines. Then we can show that there must be many more ordinary lines. So we have a bound which looks like the following. Suppose not too many points are on any plane. This 3n/4 is an arbitrary constant. Suppose most of the points don't lie on a plane. So at least some constant fraction of points is off a plane. Then the number of ordinary lines is at least 3n/2 plus some small constant times summation r square tr. So if tr is, so if you look at the number of 4-rich lines, if you have, so this is the corollary, if you have k 4-rich lines, then you have omega k, at least omega k ordinary lines. You have k square 4-ish lines. So if you have n square 4-ish lines, it would give you omega n square ordinary lines. Similar to the qualitative guarantee of Melchior's inequality, which worked in Euclidean space. And if you have even one line which has n over 100 points on it, then again you get omega n square ordinary lines because of this r square. If you have even one line with n over 100 points, you would get omega n square ordinary lines. So this is again the analog of Melchior's inequality. It looks also a lot like Hirzebruch's inequality, which was used in the original proof of Kelly's theorem. And let me just compare all these statements. So what we show that the number of, if you have points spanning 3-dimensional complex space and the number of ordinary lines is at least that expression. Hirzebruch's inequality says that if you have a set of points spanning 2-dimensional complex space, then it doesn't give you any bound on the number of ordinary lines, but it gives you a bound, it's some similar result, but it gives you a bound on the number of ordinary lines plus the number of 3 rich lines. So it doesn't tell you straight off anything about just the number of ordinary lines. So in that sense, it's a weaker statement, but it's only for points spanning 2-dimensional complex space. And Melchior's inequality is also in a similar spirit. If you have points spanning 2-dimensional Euclidean space, then you get, this is again a bound on the number of ordinary lines. So even when it's comparing with Melchior's inequality, our bound also has this r square term in front of TR instead of r. So this result is even interesting over Euclidean space.
But you're adding this condition on avoiding a plane.
Avoiding a plane is somewhat necessary. We have a counterexample that if you don't avoid a plane, then it's not true. To have that, if you have one that r square in front of TR, then you need to avoid a plane. If you put it all on a plane, then we can see that that's going to be too strong. Right. Okay, so that's the statement. We can also show that if you have points spanning 4-dimensional complex space, again with not too many on a 3-dimensional plane, then you get quadratic number of ordinary lines. Such a statement could, so like I said, such a statement could be true in 1 dimension less. It could be that if you have points spanning 3-dimensional complex space with not too many on a plane, already you get quadratic number. So the 3n over 2, I don't know if it was tight or not. So that this quadratic bound might be true in one lower dimension also, but we don't know. Okay, so what I'll tell you now, I'll give you a high-level proof of how we get this bound of 3n over 2 ordinary lines. And I'll give a very high-level sketch for why the second result, this Melchior-like result of why, if you know that there are many 4-rich lines and you get many ordinary lines, how do you use this extra information of higher rich lines to get ordinary lines? Okay, so first we'll see, so again the bulk of the proof is going to be the using rank bound techniques for analyzing design matrices. So let's see where these design matrices even come and how do rank bounds for design matrices show up in these incidence theorems. Okay, so how do we go from these incidence theorems to rank bounds for design matrices? So we'll we'll use heavily the framework of these two papers, BDWI and DSW. BDWI initially used this framework to talk about these delta Sylvester-Gallai configurations. DSW used it to give improved bounds for these delta Sylvester-Gallai configurations, as well as this new proof of Kelly's theorem. So we'll use, so here's the outline of how, what we'll do. We'll take these incidence configurations, and from that we'll construct a particular matrix. The dimension of the incidence configuration, we want to show that these incidence configurations lie in low dimensions. The dimension of the configuration will be related to the rank of this matrix. And this matrix will turn out to be something called a design matrix. And so we can argue about the rank of these design matrices using some technique called matrix scaling. So these are all the components which are going to make up. So let's see what these matrices are. Okay, so we have a config. So we are talking about complex space. We have a collection of points in the d-dimensional complex space. So say V1, V2 up to Vn are these points. And we have a whole bunch of collinear triples, right? So suppose there were few ordinary lines, then there are lots of collinear triples. Each time we get a collinear triple, if Vi, Vj, Vk are collinear, that means there is these coefficients alpha I, alpha j, alpha k in the complex numbers such that alpha I Vi plus alpha j Vj plus alpha k Vk equals 0. So you can get these coefficients, and which will capture the linear dependency between Vi, Vj, Vk. Good. So what we'll do is the following. We'll first construct a matrix V, where we put the ith row is the vector Vi. Okay, so we just stack V1, V2, V3 up to Vn in one matrix V. Then we'll construct another matrix A, which is what we'll do is for A is the following. For each collinear triple, we look at these coefficients of the which capture the collinearity, the alpha I, alpha j, alpha k, and we'll put these coefficients in, and we'll add a row with these coefficients. So for each triple, we'll add a row with alpha I, alpha j, alpha k in the ijth and kth locations. Okay, so the matrix A is the collection of all these, where the rows correspond to the coefficients of the triples. The matrix V is the collection of all the vectors.
You want to draw it?
I want to draw.
The matrix is
It's coming. So the next picture we'll just have it. There'll be a picture. So once you construct this matrix A and this matrix V, then A times V equals 0. It's easy to see. So okay, so the drawing. This is from taken from Zev's slides from a long time ago. I think this was the drawing. For each triple, you have these coefficients. You add a row in the matrix with the coefficients of the triple added in that row. Okay, so you can construct. So each row will have 3 non-zero entries corresponding to these 3 coefficients, and everything else will be 0. And then you stack up all these triples as the rows, and if you take this and you multiply it by the matrix of all vectors, you just get 0, because these vectors satisfy all exactly these collinearities. Good. So you construct this matrix A, which are the coefficients of all these triples. You have your matrix of vectors. You know A times V is 0. What we want to do is upper bound the rank of V. Right? So the argument will go like as the following. I want to show that there are many ordinary lines. So we'll say, okay, if possible there are no ordinary lines, then we want to show that the points are 2-dimensional. Okay, so we want to show that the points are 2-dimensional. That means we want to show that this matrix V has low rank. The rank is at most 2. To show that the matrix is low rank, it suffices to show that A is very high rank, because A times V is 0. So if A has really high rank and A times V is 0, then V must have low rank, and then we'll be done. So now all we need to do is to lower bound the rank of A. A was this matrix of these triples, again these coefficients in the triples. So now our job is just to how to lower bound the rank of A. A can be chosen carefully to become so that it's a design matrix. It turns out is a bad phrase. A is not automatically a design matrix, but we can do something. We can choose the triples in some careful way so that A is a design matrix. And once A is a design matrix, we'll see what we can do to talk about the rank of A. So what is a design matrix? So I'll say a matrix is a KT design matrix if the following holds. The property of being a design is just a property of the zero non-zero structure of the matrix. Look at what entries are 0 and what entries are non-zero.
So just one question. So what is your assumption now? About you just assume that there are many collinear triples? Like this is
yes, many collinear triples. That's the only assumption. It's a very few ordinary lines.
okay.
So
And from this you go
from this I want to I take that, good, and I construct this matrix with all the triples, and I want to say that's very large rank. That's the only assumption I make is few ordinary lines. Then I create this matrix of all the triples.
Yeah, but so what you will get is that if there are many collinear triples, then the points must lie on the plane.
That's what I want.
Inequality that you stated before about the number of ordinary lines, and right?
the number of ordinary lines plus the 4 rich lines at big inequality. Yeah, so let me not talk about that theorem. I'll mention it right at the end. Now, for now, let me just say that there are at least 3 n over 2 ordinary lines. So if the points span 3-dimensional space,
so
from this thing I want to directly conclude that if the points span 3-dimensional complex space, then there must be at least 3 n over 2 ordinary lines. And then I'll say a little bit about how to get the improved bound, and this will basically be the argument for that too. But maybe it's better to discuss it separately. But it's going to be the same framework, exactly the same framework. That if the number of ordinary lines is less than that big expression I talked about, in that inequality, then the rank must be also very large. Okay, so a KT design matrix is, just look at the 0 non-zero pattern, and I want to say that every column has many non-zeros, at least k non-zeros in every column, and every pair of columns, if you look at their intersection, then the intersection is at most t, the number of non-zeros in which lie in both the columns. That's a KT design matrix. And most previous works we needed the parameters k and t. The k was large and t was small. In this work somehow we won't really care so much about k. Let's just interesting parameters t. You almost forget about k. The design matrix is a matrix. If you look at the collection of look at the 0 non-zero pattern, then for every pair of columns, their intersection the intersection of the support is small. Forget about k most basically. That's the only property. That's what it means to be a design matrix. Yeah. When t is 1, it looks like sort of like an identity matrix, right? You can find a diagonal. Maybe it's easy to argue about the rank. But when t is that's when t is 0. Sorry, when t is 0. When t is 0, it's easy. Once t starts getting larger than 0, we have to see how do we argue about the rank. But when t is 0, arguing about the rank is trivial. Good. So I said, A was this matrix of triples, right? Where we added for every row the coefficients of the triples. How do we select what triples to add to A? If you add all the triples to A, we want this matrix A to be a design matrix, because we know we can perhaps argue about the ranks of design matrices. So we want this matrix to be a design matrix. It turns out if you add all the triples, all the collinear triples we toss into the matrix as different rows, then the matrix won't be a design matrix. So what we do, So
you can say why. I mean, if there are many points on a line.
So let me tell you why. Suppose you have r points on a line, and you toss all the triples, all the r choose 3 triples corresponding to these r points. So they are about r cube triples corresponding to the point. So then for every pair of points on the line, that pair of points is involved in about r triples, right? So if a pair of points is involved in r triples, now let's go back to this matrix. So you have this matrix A. Okay, the columns are indexed by these points. The rows each row corresponds to a different triple, and we added the coefficients. So each row corresponds to a particular triple involving some points. Now V1 and V2 are involved in many triples, and we added all those triples into the matrix. Then there will be some triple V1, V2 something, V1, V2 something else, V1, V2 something else. So for each triple that V1 and V2 are both involved in, that contributes 1 to the intersection of the columns of V1 and V2. So if V1 and V2 are involved in R triples, the 2 columns corresponding to V1 and V2 intersect in R locations. So for this matrix to be a design matrix, what we will want is that V1 and V2 both sit in very few triples. So for each pair of points should sit in very few triples, and what we'll do is we'll construct this matrix A. So if there's an R rich line, we don't want to add all those R triples because then it won't be a design. What we'll do is we'll make sure that every pair of points will sit in exactly 6 triples in this matrix. Okay. the points which are which correspond to an ordinary line, they will not sit in any triple. So those pairs of points don't have any intersection, but the pairs of points which are not on an ordinary line, we'll make sure that they line exactly 6 triples. The way we'll do this is the following. If there's a pair of, if you have a line with exactly 3 points, then we take that triple and add that triple 6 times to the matrix. So now all the pairs of points on that line got counted 6 times. If you have a line with more than 3 points, even a line with r points, then we won't add all the triples on that line to the point. We'll carefully choose some subset of triples from that line, and that we'll choose it carefully so that each triple is added. Each pair is added. For a line with 3 points, we add the triple 6 times. If you have a line with many points, we'll pick a family of triples from that line, and that family will be clever so that each pair occurs in exactly 6 triples. And you can do this using some Latin square combinatorics for the points on the line. So a carefully chosen subset which will give you exactly every pair occurring 6 times. And once we do this, so once we ensure that each pair of points occurs exactly 6 times in exactly 6 triples of the matrix, we can do a careful counting, and it will tell us that the number of rows in this matrix is exactly n square minus n minus 2 T2, where T2 is the number of ordinary lines. Okay, and why is this? So each row of the matrix gives you 3 pairs. Right? So the total number of pairs in this matrix is 3 times m. Okay. Let's count the number of pairs in a different way. Each pair which is not on an ordinary line gets added to the matrix 6 times. So the total number of pairs not on ordinary lines are n choose 2 minus T2. Right? Because they totally n choose 2 pairs, and every pair not on an ordinary line is n choose 2 minus T2. So you take n choose 2 minus T2 and you multiply it by 6, that equals 3 times m, and that gives you an exact bound on the number of rows of this matrix in terms of the number of ordinary lines overall. Okay. So this bound will be important.
Quick question. So isn't it true that a pair of points can align multiple lines, and then your procedure added multiple?
So a pair of points cannot line multiple lines, right? So that's good question.
Okay.
Important question. Yeah, but that's really important too. So hence we can just break up this problem line by line. For when we add triples, we can just go to different lines and focus on that line and add triples corresponding to that line, and the pair will just come from a particular line. Yeah. So hence we know the bound on the number of rows in terms of T2. So these earlier works, BDWI and DSW, now said, okay, now suppose, so this matrix we got was a design matrix. Was the I'm not telling you, we don't really know what K is out here, right? K was the number of non-zeros in every column, and I said let's not care too much about it. All we know is that every pair of columns intersect in T in 6 locations. If we knew information about K as well, which sometimes we do, then these works, BDWI and DSW, said that if you have a KT design matrix, then the rank must be at least that. Some expression like that. So if K is linear in n and T is a constant, then this term is just a constant, and then the rank is n minus a constant. And so that was a kind of rank bound that was proved if you have a KT design matrix, and these hold for characteristic 0, don't hold for small characteristics, etc. We won't take this exact bound because I don't want to use K at all. I just want to focus on T. But we'll use this the same techniques will be used, or similar techniques will be used to give the bounds for our case. But we don't know any information about K now. Okay, so how do we prove a rank bound? Now we don't have a KT design matrix, we basically have this T design matrix. So we know that every pair of columns intersect in 6 locations. And I want to show that the rank of this matrix is really large. How do we show the rank is really large? So first, the easy case. Let's pretend for now all entries are either 0 or 1 in the matrix. So if all entries are either 0 or 1 in the matrix, how do we bound the rank? Let's look at A transpose times A. Okay, so that gives you a square n by n matrix. I want to show the rank of A is very large. If I can show that the rank of A transpose times A is very large, then that will tell me that the rank of A is very large. So let's look at the rank of A transpose A, and what are the entries of A transpose A? So the ijth entry is the inner product of the ith column of A with the jth column of A. And if all the entries are 0, 1, then on the diagonal, if it was a KT design matrix, if you knew that all the columns had many non-zeros, then the diagonal would be large, and the off diagonal would be small, because the supports of every pair of columns intersect in any t location. So every off diagonal entry would be at most t. And so this matrix has very heavy diagonal, very light off diagonal. It looks like a perturbed identity matrix, and we know techniques for bounding the ranks of perturbed identity matrices. In particular, if you have a Hermitian matrix, so A transpose A was a Hermitian matrix. If you look at A transpose A and you know that everything on the diagonal is large, then you can bound the rank by this expression. It's n times the diagonal, the magnitude of the diagonal square divided by something something something. You can just take this technique, which a simple this is very simple spectral argument to get this inequality, and you can use it to bound the rank of a perturbed identity matrix. What you need to show is the sum of squares of all the off diagonal entries is small, and the sum of on all the diagonal is heavy. You can just combine it to get your bound, and this is the inequality that we use. Okay, so this is the main inequality used. In general, of course, you don't have 0, 1 entries, so your matrix may not look like a perturbed identity matrix, because if your matrix has, and this was taken from Zev's slides from long ago, if your matrix has all kinds of wildly skewed entries in it, and then now you look at inner products of pairs of columns, you can't say anymore that the diagonal must be heavy or the off diagonal must be small, because now the entries look pretty wild. So the hope now is, what was again the plan which was executed in the BDWY paper, was to use this technique of matrix scaling to somehow tame this matrix. The entries look really wild here. Let's scale the matrix, and by scale what I mean is the following. We'll take all the rows and multiply them by positive real numbers. Take the columns, multiply them by different positive real numbers. So each entry, the ijth entry, is replaced by the original value times Ri times Cj. These are positive real numbers. Notice that if the rank, when we just multiply the rows by scalars and the columns by scalars, the rank of the matrix doesn't change. The rank stays the same, and the support of the matrix stays the same. The 0 entries remain 0, the non-zeros remain non-zero. So a design matrix remains a design matrix. So this operation we can just do by free. If you want to just bound the rank of design matrices, this scaling doesn't cost us anything. And it turns out that there is a scaling which you can apply, which will somehow make the matrix a nice matrix and make all these coefficients, the entries of the matrix, more balanced. And so there's the theorem that is used is the matrix scaling theorem. And if Avi has not already told you about it, go ask him. He's done a lot of beautiful work with the matrix scaling theorem. And the theorem is the following. Suppose you're given a matrix A with non-negative entries, and suppose you know that there is no large submatrix which is all 0. So any non-zero, every minor or every submatrix of this original matrix which is all 0 must satisfy that A over M plus B over N is less than 1. Okay, so there's no large matrices which are all 0. Then you can scale, you can find these coefficients to multiply the rows and columns by, so that all the row sums become basically the same and all the column sums become the same. statement is clear. And you can also apply this matrix scaling theorem after squaring the entries of the matrix. So basically you can do the scaling to get the L2 norm of all the rows be the same and the L2 norms of all the columns be the same. Okay. So that's the matrix scaling theorem we're going to use. So we took a design matrix and we scaled it. I say it's a KT design matrix, but for now you can forget, there's no K. It's a T, so the entries, every pair of columns intersect at most T locations. And you took a matrix and you scaled it, and so now all the row norms became the same and all the columns norms became the same. So suppose the scaling was chosen such that all the row norms are 1, then the column norms will become exactly m over n. And they're also all the column norms are m over n, all the row norms are 1. And now let's do the same. Now this is, instead of 0 1 matrix, we have an arbitrary matrix with this property, and now let's look at, and say we're over the complex numbers, so let's look at A star A. So A conjugate times A, and we want to bound the rank of A, so we'll bound the rank of this product A conjugate A. And what is the matrix that you get, the n by n matrix? What is on the diagonal? The ith entry is just the inner product of a column with itself, which is just the L2 norm of the column. So that's just m over n. Right? So all the column entries, the diagonal entries are exactly m over n. What are the off diagonal entries? It's not, it's something. Hopefully it's small. We have, so hopefully we can use this design property to argue that the off diagonals are small. And if you can argue that the off diagonals are small, then this gives us again a perturbed identity matrix, and then you can use the same inequality to bound the rank of the matrix. And since we know that what the entries on the diagonal are, MII is exactly m over n, let's call it L, we know everything in this inequality except this summation mij square. So as long as we can show the summation mij square is small, we can plug it in and hopefully get a good bound on the rank. So the smaller you can make mij, the summation mij square, the larger, the better the bound you can prove on the rank. And so this kind of this was again used in the earlier works. BDWY gave a bound. There's a trivial bound of T you can place on every off diagonal entry. Since all the row norms are 1, that means all the entries of the matrix are at most 1. So Ci times Cj will be at most T. So you can use a bound of T. In DSW we gave a strengthened bound on the sum of squares of these off diagonals, which gave us improved rank bounds. So let me just recap again, a quick recap of what the shape of the proof was, and now let me say where our improvement really comes from. So we start with the matrix, where a matrix of all the vectors, all the VI's, that was V. A was the vector of all these coefficient triples, which we chose carefully. We didn't take all the triples, but we chose it carefully so that each pair appears few times. AV was 0. We want to say that this matrix V is two dimensional if there are not too many ordinary lines. So if T2 is small, we want to say V is low dimensional. So in particular, we want to say that we will conclude this by showing that A is very, very high dimensional. A is a design matrix, and we want to say that this design matrix A is high dimensional. We will scale the matrix so that the row norms are 1, the column norms are m over n, and we can do this if A satisfies property S. We can't always do this. If this property S was the property that there's no large submatrix which is all 0. So there's no large submatrix which is all 0, then we can scale the matrix and have the row norms, column norms be the same. And then we look at A star A, it looks like a perturbed identity matrix, and so it has very high rank, and so we're done.
So again, how did you get rid of this K? I mean, why?
There was no K. This bound, I need to bound mij square, and as long as when I bound mij square, I don't use K.
But isn't it needed for the diagonal to show it?
No, the diagonal was m over n. It didn't. There was no K, right?
Okay, but K was used to get the property S.
Good. K was used. Good. So right now there's no K showed up. So the property S is something which I've been hiding under the rug. We can only scale the matrix if it satisfies property S. So that means there is no large submatrix of all zeros, and we have to handle property S. We have to handle property S somehow, but no K was needed in this proof. The diagonal entries were M over N. I need to know what M is. In earlier proofs, maybe the bound on M also came from K. You used the information about K to say that M is something. Right now, we got a bound on M independent of K, because M was at n square minus n minus 2 T2. We have a precise bound based on the number of ordinary lines. So K disappeared. And in this argument, there was no K anyway, because on diagonal was M over N, because all the column norms got scaled to be the same. And off diagonals are small, as long as we can bound this without using K. And in the earlier works, they were bounded without using K. So no K was needed. So as long as your matrix satisfied property S, this was it. You just scale the matrix, pray that it satisfied property S, and if it did, then you just use these same calculations and this exact bound on M, and then you just get that T2 has to be 3n over 2. And property S turns out to be, okay, what if it doesn't satisfy property S? So in earlier works, so this property S is this, for scaling, we needed the matrix to satisfy property S, and in the way the earlier works ensured it was, you look at all the rows of your matrix A, and then you repeat different rows with different multiplicities and use the bound on K to show that you can do this without too much loss. And so you make it satisfy, you force it to satisfy property S, and then proceed the same sketch of argument as before. But now we don't want to do that. If you already satisfy property S, again we know what to do. Let's not force the matrix to satisfy property S. Let's say, okay, what happens, what does it mean that the matrix doesn't satisfy property S? Let's try to understand the structure of a matrix not satisfying property S and try to use that to our advantage. So if it satisfies property S, we're done, and if it doesn't satisfy property S, I want to say we're still done, but for a completely different reason. Okay, so what if the matrix doesn't satisfy property S? This means that there's a large submatrix of zeros. That's a lot of structure. So maybe you can use all those zeros to our advantage. So you take a large submatrix of zeros. It's an A by B submatrix, which is all 0. That's that yellow matrix. What does it mean that there's a large submatrix of zeros? It means the following, right? So this matrix of zeros is x times y. For all the points in y, the columns are indexed by the points in our configuration. For all the points in y, those points don't contribute to any of the triples up to here. The points of y only contribute to triples in this lower part. So all the points in y don't line any of the triples corresponding to the rows of x. So the points of y only touch the triples from here, and the number of triples out here is m minus a. This is the information I want to use. That there is this set of y where they only touch few triples. And let's take a very specific case. Suppose y equals 1, size of y equals 1. So there's only one point. So this matrix of zeros is a long skinny matrix. So we have only y is 1 corresponding to a single point v. Since A over m plus b over n, this long skinny matrix has to be a big matrix, this criterion means that the size of x needs to be really large. A needs to be at least 1 minus 1 over n times m, which is the same as saying that this portion, since we know that m was at most n square minus n minus 2, so m is less than n square. This was a bound we knew from before. This tells you that m minus a, this portion out there, is at most n. So that point v touches at most n triples of the matrix. Okay, so v must mean at most n triples. Hence this point v is involved in at most 2 times n pairs appearing in the matrix. For every triple, the point contributes 2 pairs to that matrix. So v is involved in at most 2n pairs in the matrix, and each pair was tossed in 6 times. Right? So it's the at most n over 3 distinct pairs that v is involved in. But if v is involved in at most n over 3 pairs, and these pairs are the pairs which came from the non-ordinary lines, then what about all the other pairs we could have been involved in? We can consider a pair V with any other point in our point configuration. Only n over 3 of these sit in this matrix. That means only n over 3 contribute to these non-ordinary lines or the special lines. The remaining 2 n over 3 pairs which didn't appear in the matrix were exactly the ordinary lines. So this point V must lie in 2 n over 3 ordinary lines. That's the only way it could happen. So you're giving one long skinny matrix of zeros gives you one point which is involved in many ordinary lines, 2 n over 3 ordinary lines. And that's basically the main observation. Now we just take the same argument and say, okay, what happens when that y was more than 1? When y was equal to 2, almost the same analysis will give you 1 point with 2 n over 3 ordinary lines. You do it carefully. When y is 3 or larger, in fact, we can not just have 1 point with many ordinary lines, we can directly do again some simple inequalities of that earlier kind to get at least 3 n over 2 ordinary lines or more. Okay, so basically what we can show is that suppose your matrix doesn't satisfy property S, so you have a big 0 matrix, then either you have enough ordinary lines and you don't have to worry, so you either already get the 3 n over 2 ordinary lines, or you have 1 point. This is the case when the size of y is 1 or 2. You have 1 point through which there are many ordinary lines. Either you're done or there's 1 point with many ordinary lines. And if you have 1 point with many ordinary lines, then you just take that point, throw it away, and recurse the same argument on the remaining n minus 1 points, and you'll get 3 n over 2 ordinary lines pretty easily. This delete and recurse step is fairly straightforward. And so that's basically the proof, the full proof. We use the similar framework to before, but we don't use the information on K to force property S. But we just see that, okay, what if it doesn't satisfy property S? Then let's get additional structure from that matrix and get the ordinary lines another way. And so that's that theorem. So basically you get the 3 n over 2 ordinary lines unless many points are in a plane in which you get fewer ordinary lines. This delete and recurse process will stop if when you delete that point, all the points become coplanar, the remaining points. So that's where this other condition comes. There was this other theorem which gives a strengthened bound of 3 n over 2 plus this expression. Okay, let me have the 5-10 minutes. So let me just give a hint at how you get this improved bound. So 3 n over 2 was what came out of this argument. How do you get many more lines? In particular, if you had omega n square 4 rich lines, how can you use it to use that information that there are lines with more points on them, use it to extract even more ordinary lines? Okay, so basically the recap, the skeleton of the proof is going to be the same. Let me tell you where the change is going to occur. Okay, so again you have all your points, you construct this matrix V with all the points as rows, you construct the matrix A where you choose the coefficients of you add triples carefully so that every pair occurs in exactly 6 triples. A times V is 0. We want to say if the number of ordinary lines is small, then the points are 2-dimensional. Okay, so we want to say that if you don't have enough ordinary lines and V is 2-dimensional, so we want to say if the number of ordinary lines is small, then the rank of A is really large. A is going to be a design matrix. Again, forget K, we just care about T. If the matrix doesn't satisfy property S, then we can use the structure of the matrix, the lots of zeros, to extract single points with many ordinary lines and do something. This step is more involved because you need to show more ordinary lines. But again, if it doesn't satisfy property S, we can look at those lots of zeros and work with that in a combinatorial fashion to just get either many ordinary lines or points through which there are many ordinary lines, and then we can use the recurse step. But what if it satisfies property S? How do we get more ordinary lines than we could have done before? Even if it satisfied property S, before we could only guarantee 3 n over 2 ordinary lines. Now I want to guarantee many more than 3 n over 2 ordinary lines if we have these 4 rich, 5 rich lines. So how do we use this information that there are lines with many points on them to get an improvement? When we used So how did we argue that the rank of A is large? We said that, look, let's look at A star A, and it looks like a perturbed identity matrix. Right? So it looks like a perturbed identity matrix, A star A, where on the diagonals you had m over n, and off diagonals you had something else. And so we needed to get a bound on the summation mij square. If you can get a better bound on mij square, you can show a better lower bound on the rank of A. So we want to give an improved bound on this quantity, summation mij square. Because the moment any improvement on that gives you more leverage to work with, because you can get a low bound on the rank of A. So we want to use the fact that you have lines with many points on them to get a better bound for this quantity. So what does summation m, you want to minimize summation mij square. What is mij? Is the inner product of the ith column with the jth column of the matrix A. We want these inner products to be as small as possible. Okay, so let's take, again, I have k but forget k. You just take two columns and you want the inner product to be as small as possible. If I take the inner product of two columns and I want it to be small, one way the inner product could be small is if I have a plus plus and a plus minus. Right? If I look at the inner product and you have different signs, suppose we are not over the complexes, for now we are over the real numbers, and we have different signs occurring amongst the entries here. So there's some plus plus and there's some plus minus. Then when we take the inner products, the plus might cancel out with a minus, and these cancellations might give you smaller inner products. Right? If the inner product was 6 and all these entries were 1, 1, 1, 1, 1, 1, 1, 1, 1, then this inner product would be 6. But if you have all ones out here, but 3 of the ones have a minus sign, then the inner product can be 0. So hopefully we can take advantage of different signs, plus minus signs, to get cancellations in these inner products and show that these inner products are much smaller than we could show earlier. So that's going to be the hope. We get lots of plus minus sign cancellations. And when can you have these sign cancellations? Suppose you have a pair of points, so that the line through this pair contains exactly 3 points. So it's a 3-rich line. Then how does this pair appear in the matrix? We just take that triple and we repeat it 6 times, because that pair had to appear 6 times. If we just take one triple and repeat it 6 times, then if you look at the corresponding pairs, then there won't be any sign cancellations, because it's the same pair appearing 6 times. So there's no cancellations. But if you have a line with 4 points on it, then maybe we can hope to get cancellation. And again, this is why we get cancellation. Suppose you have a line with 4 points, v1, v2, v3, v4. Now let's focus on the points v1, v2 and look at what triples we add into this matrix. We have a triple corresponding to the v1, v2, v3, and we have a triple corresponding to v1, v2, v4. And for now, let's assume we are over the real numbers. v3 is in between v1 and v2, and v4 is outside v1 and v2. Suppose you're in that setting. Then if you look at the triple v1, v2, v3, the coefficients of v1 and v2 will have the same sign. And if you look at the triple v1, v2, v4, the coefficients of v1 and v2 will have opposite sign. And that's why when we put in both these triples into the matrix and you look at the inner product of the two columns corresponding to v1 and v2, there'll be some cancellation. And that's how we gain. So when we have, so we gain, and this was for 4-ish lines, for r-ish lines, we can extend this. A similar thing will extend. Good, let's leave that out. So basically now we have to quantify what the gain is. What if v1, v2 were, if v3 and v4 were both outside v1 and v2, then we don't gain. So how many pairs of points are there where we have triples with some point in and some point out? So we need to construct, for every line we need to construct a triple system of families carefully, so that there are many pairs where the triples have 1 point in and 1 point out. And so once we have, then that way we want to do that, choose our triple systems to maximize cancellation of this kind. And we have to quantify that cancellation, and when we put it all together, that's the inequality that we get. So for R rich lines, we can get better cancellation than when for larger values of R. But once you have this idea, then you just have to chug through it and be brave and do the calculation. This idea was basically the main step in the argument, that you can get cancellations using this method. And this sign cancellation is specific to the reals. For complex numbers, you can, instead of talking about plus minus signs, you can talk about angles between complex numbers. And so this entire thing can be extended, instead of talking about pluses and minuses, about angles between complex numbers. And so that needs a little bit more work, but again, there's no new idea there really, it's a calculation. And so then that's how we get the improved bound. And just let me end with questions. Are these bounds tight? Absolutely no idea if the 3n/2 is tight, or is the quadratic the better bound. All these results I talked about complex space, these are all new results even over Euclidean space. So point spanning 3-dimensional Euclidean space has 3n/2 ordinary lines. It was also a new statement. So maybe you can get improved bounds for Euclidean space. Maybe 3n/2 is not the best bound there, but you can do something more clever to get better bounds for Euclidean space. I don't know. Can you construct, careful using elliptic curves and extensions of them, construct special configurations of points with few ordinary lines? That's a great question, and we have nothing non-trivial at all. And can we use again these methods, the fact that if you don't satisfy property S, then you look into the structure and get something more, can we apply it to other places where the rank bounds have been useful? And that's again an interesting direction. So I'll wrap up there. Thank you.